Guys, this course on ray optics and optical instruments has been divided into two parts, and this lesson shall be the final one in this part of the course. We are going to learn about total internal reflection and its myriad applications. This course has been designed and taught by myself, Samip Velani, and if you like my work and would like to give appropriate ratings and would like to express your pleasure or displeasure in the form of comments or reviews, please follow me on this link and watch my lectures and courses. And doing so, you'll be notified about my future lessons and courses as they come live on the Unacademy platform. Make the most use of this. Let's start with the guiding question. This here is Blackie, a black triggerfish living peacefully in the coral reefs off the coast of Maldives in the Indian Ocean. They are known to be very aggressively protective of their eggs and spawn, and can ward off most predators by a deadly and sudden show of its two dorsal spines, the second being wielded only when the first spine show does not work. So when the first one fails, the second one springs up. So you have two foes against a predator, hence the name triggerfish. The first one's failure triggers the second one to come up. The question is, how are we able to see the inverted reflection of Blackie on the water undersurface right above it? Now we see the fish obviously in the camera, but why are we seeing this part here? What is causing that? And for that matter, how is this image on the right produced? That is, how are we able to see the swimmer on the water-air interface right here? We can obviously see that this is the actual swimmer. What is causing this to come up? More importantly, does this phenomena depend on where the photographer is relative to the swimmer? Think about it. The reason is really interesting. Let's put a deep foundation on what total internal reflection really is. Now, when light is traveling from a optically denser medium such as water into an optically rarer medium such as air in this case, it gets refracted away from the normal at a certain refraction angle theta 2 here in this case. As the angle of incidence in the denser medium increases, the refraction angle also increases, and eventually the refraction angle becomes 90 degrees. That is, the refracted ray goes parallel to the water surface, travels parallel to the water surface. That is, the normal and the refracted ray are perpendicular to each other for a certain incidence angle called critical angle. For every incidence angle greater than critical angle, you will see all the light rays that are incidenting on the water-air interface to be totally internally reflected. An important criteria in this case is light must pass from an optically denser medium to an optically rarer medium. The reflected portion of the incident light is usually less intense, as in this case when the incident ray incidents on the media interface, some of it is reflected, most of it is refracted. But in the case of total internal reflection, there is no refraction. All of it is getting reflected back into the water. In this case, Snell's law of refraction does not hold anymore for angles of incidence greater than the critical angle, and the law of reflection starts exhibiting itself. That is, the angle of incidence is equal to the angle of reflection, which is exactly what you see here. The angle of incidence becomes increasingly similar to the angle of reflection, as you see here. How do we define the critical angle of incidence? The critical angle of incidence is given by theta c. The sine of theta c is equal to the refractive index of air with respect to water. Now, refractive index of air with respect to water will be less than 1. And that is exactly what sine theta c will be. It's always less than 1. Sine of any number is always less than 1, or less than or equal to 1, that is. So this comes from Snell's law, because here you have sine I by sine r, where sine r for the critical angle is 1 for 90 degrees. Or in other words, The refractive index of glass or water, the denser medium with respect to the rarer medium, is inversely proportional, or it's just the reciprocal of the sine of the critical angle. The refractive index is the reciprocal of the sine of critical angle. Higher the refractive index of the denser medium, lower the critical angle, greater is the probability to achieve TIR, or total internal reflection. Let's revise what optical density really is. We have done this in the past, just revising. Optical density is the ratio of speed of light in the first medium. Here the first medium is the rarer medium, to that in the second medium, which is here the denser medium. You may interchange it according to your needs, where the refractive index of the denser medium with respect to the rarer medium is given by this, and refractive index is a measure of the optical density. Usually optical density is proportional to mass density of the medium, but that may not always be the case. Find out why. Let's demonstrate how total interreflection is achieved. When a laser beam is incident on one of the end faces of the glass pipe at an appropriately low incidence angle, as in this case, the incidence angle should be as low as possible. To achieve something else, we'll know soon, where the normal is drawn perpendicular to that face, which is the white dashed line you see here. The refracted ray that enters the glass pipe, which is this one right here, which you can see because of the impurities in the glass, the refracted ray incidents on the glass air interface, which is this point here, at a sufficiently large incidence angle such that it exceeds the critical angle, and hence total internal reflection occurs at this face. Also occurs at this face, also occurs at this face, because the angle of incidence is equal to the angle of reflection. You will keep on getting total internal reflection as long as the pipe subtends. Now, the most important, widespread and critical application of total internal reflection is in the case of optical fibers, which are means of transporting information or just light, information on light. That is, when you want to send information through light, you modulate the information that you want onto the light frequency, and then you send it along the optical fiber. An optical fiber is just a light pipe. It transports light from one end of the world to the other end of the world without or with least amount of loss, because most of the energy is reflected and nothing is absorbed. At least most of it is not absorbed. Most of it is transmitted along the optical pipe or the optical fiber. This is used for long distance communication and information transfer, as in the case of the internet. Nowadays, the internet, you don't use copper or metal cables, you use optical fiber cables, so that you will know what your brother in USA is doing right now through your Skype call. That happens only because of optical fibers. The desert mirage is another optical illusion caused as a result of total interreflection. When it's a very hot day during a sunny day, the land in a desert is usually pretty hot because land does not give out heat very easily. It retains the heat for a long time. As a result, the air surrounding the land will get heated up. And due to this heating up, the air molecules will be as far apart as possible, which decreases the mass density of the hot air. And the cool air above the hot air layers has a larger density, and here in this case the optical density is proportional to mass density. So as you go higher and higher in the atmospheric layers, your refractive index is increasing. So suppose a light ray is coming from this tree towards a light ray is traveling in this direction. Because the refractive index of this layer is greater than this layer, the light will increasingly bend away from the normal, and as a result, slowly and eventually it will totally internally reflect back into the air, as if it will reach our eyes in a sense that we would feel that the tree is somewhere here. In fact, the tree is somewhere there. So to give you a feeling from this image, maybe the trees that I'm looking at right here, the buildings, the trees, everything, maybe they are not actually there, they are here. So the light coming from that mountainside down towards the ground is being reflected, totally internally reflected back into my eyes, to give me an elusive picture that the buildings and trees are actually down here instead of back there. So this is an optical illusion, which is what you usually also see during humid days on a long stretch of road. If you are at a place and you're driving on an empty road, you will see some wet surfaces very far away on the roads. And when you really approach that place, you see that there is nothing wet there. There is no source of water. Where did the water go? You did feel something wet there. What happened? That is an optical illusion, also a mirage. Another application of total interreflection is in the case of rain sensors on windshields, which automatically actuate the wipers to clean the water droplets from the windshield when rain occurs. That is, when there is no rain, that is, there are no water droplets here on the glass surface, there is total interreflection, which is caused as a result of the light incident because of the LED lamp. And all the light is absorbed by this sensor here, or a photodiode. But when there is water on the surface, the refractive index of glass with respect to water is lesser than glass with respect to air. And as a result, the critical angle is larger. Lesser refractive index, higher critical angle. And for that reason, for the same angle of incidence that you had earlier, some of it will get reflected, but some of it will also get refracted. So the intensity of passing light decreases. So that decreased intensity will actuate the wipers to move. As a result of refraction, total internal reflection is the best method to get the least amount of loss on reflection. If you use mirrors in periscopes, as in this, mirrors also absorb the light. So your light intensity is going to undergo some loss. But in the case of total internal reflection, there is no loss. You get a lossless image through the periscope if you use prisms, that is, solid transparent media instead of mirrors, reflecting media. You have an improved periscope. Thank you for listening. If you have any questions, please ask in the comments section. And I ask you to kindly brainstorm about what you have learned so far for a few minutes. There are many more applications of total internal reflection, and I want you to think about them as much as possible. This topic, this lesson will also help you to solve the guiding question that we have approached, that we had come across in the past. How are you able to see or detect those cancer tumor cells in the lungs or anywhere in the body by using the concepts that you have learned already? What technique are you going to use that will help you to see those tumorous cells with visible light? Thank you.